In this presentation, I'm going to talk to 5 points that we elaborate on in the briefing paper, and then Paul will actually talk briefly after me about some of the research that we do in the department in terms of capture. So the first point, which Martin made very well, was that CCS is only one part of the solution to mitigating climate change, alongside renewables, alongside nuclear, not in opposition to. Now, CCS is best applied to large point sources, and a coal-fired power plant is a very good example of a large point source. But there are other examples, including gas and biomass-fired power plants, but also in industry, industrial boilers used to raise heat for industrial processes. If we agree on the fact that CCS is an important part of the solution to mitigating climate change, well, then the next thing we need to do is get around and do it and sort of accelerate the full-scale deployment. There are no major technical barriers to doing this, but there are technical uncertainties. The technical uncertainty because we haven't yet demonstrated capture integrated with a full-scale power plant. But the major uncertainties are associated with the cost, and this is to do with a lack of clarity in terms of policy and regulations. And finally, there is a need to reduce the cost. The capture is the most expensive part of the project. So there's a real need for sustained research effort in this area to reduce the cost of capture, which has significant economic implications over the lifetime of the project, which is likely to last 30 or 40 years. So I'm going to breeze through this very quickly. This figure here shows the CO2 emissions associated with the combustion of fossil fuels, with the combustion of conventional fossil fuels. And the trend is associated with the spread of industrialization across the globe, and it's also sustained by trends towards modernization and electrification. And so most of these emissions are in fact associated with the electricity sector, the electricity system, and it's a system that we just can't turn off instantly, and we can't turn it off instantly because we can't turn on nuclear power and renewables to meet the demand that's growing. And furthermore, we need to do something about the emissions being produced now by our fossil fuel plants, and also the emissions that will be produced by the plants that we're building today into the future. So I've included a very simple analysis here to sort of demonstrate the extent to which CCS might be important. And so the first number, the 80%, is the share of total greenhouse gas emissions that's CO2. 60% of these emissions are associated with large point sources. So this is where CCS is most applicable. And if we make a very optimistic assumption that we get a 90% coverage, and that we're capturing and storing 90% of the emissions from these point sources, then we get to a reduction of about 40%. And of course, this is unrealistic. It's a big number, but it's an unrealistic number. If we make more reasonable assumptions, and perhaps the coverage is closer to just over half, 60%, and we're not capturing all the emissions due to emissions associated with mining and the transport of the fuel, then the number's closer to 20%. And that's a big fraction, but it's clearly nowhere near enough of the reduction that's required to meet the 80% reductions that are being discussed around the world. So I'm just hammering the same point, really, that CCS is only one part of the solution, but it is an important part of the solution. So we've seen this image before. CCS can be applied in many different ways. So at the centre here, the CO2 is being captured from coal, gas, biomass-fired plants, and industry. The CO2 needs to be purified, compressed, and then transported. Martin talked about enhanced oil recovery, and this is a very mature industry at the moment. there are other reuse options which are being considered, including using CO2 to make plastics and fuels. But these reuse options are not part of helping climate change, or helping mitigate climate change. The demand is just not at the same scale, the amount of CO2 that we're producing for these power plants, and so most of the CO2, a significant fraction, needs to be stored. So as you can see, there are many different ways in which CCS can be applied, and dependent on the application, the mitigation potential is quite different. And life cycle thinking is important to assess this. So a coal to liquids process with CCS fitted is still going to release CO2 into the atmosphere. However, at the other end of the spectrum, there's an example where CCS can be integrated with bioenergy systems and effectively remove CO2 from the atmosphere. This is perhaps one of the more practicable examples of an air capture system. Certainly more so than direct air capture systems. It's always going to be cheaper and more efficient to use CCS coupled with a biomass-fired power station. So the advantage of these type of technologies is it can be potentially used to offset emissions in different sectors, which are hard to get to, but it also can be seen as a tool to regulate the rate of mitigation. Of course, there are limitations on the application of this related to the sustainable production of the biomass and the transportation of the biomass. And another application of CCS is in industry. And industrial emissions represent a significant fraction, about a third of total CO2 emissions. And some of these emissions are hard to get at, if not impossible to get at, without fundamentally redesigning the industrial process. And cement's a primary example. Firstly, it represents about a quarter of the total emissions, but the chemistry behind cement manufacture means that we're limited in the extent to which we can mitigate these emissions by measures such as energy efficiency or fuel substitution. And that's because the first step in the process is the decomposition of limestone, which is calcium carbonate, and that gives off about 50% of the emissions. So these emissions can be managed by integrating the process with cement, and in fact there's a unique synergy with the cement manufacturing process and calcium looping, which is a capture technology that I'm involved in investigating in the department. And there's posters outside if you want to learn more about that. But the next part of the presentation, I'm just going to give a bit of an overview of the different capture technologies. So there are three main categories: post-combustion, pre-combustion, and oxy-fired combustion. Some of the more advanced capture technologies sort of borrow elements from these different categories. But at the core of all these processes is gas separation. So for post-combustion, it's the separation of CO2 from nitrogen. For pre-combustion, it's the separation of CO2 primarily from hydrogen. And for oxy-fired combustion, it's the separation of air from nitrogen. And what these processes have in common is that they use energy. So if you're thinking of applying this process or integrating this with an industrial process or a power plant, there's going to be a parasitic energy demand on the process, and that's a real driver for research in this field. So this diagram shows post-combustion capture. This is an end-of-pipe solution, literally because with this process we remove CO2 from the exhaust of a power plant. And there's an advantage here in that this technology is retrofittable. It doesn't require significant changes to the power production process, other than reducing the energy output. So the main technology used here uses amine-based solvents to capture the CO2. And these capture systems have been used for decades in the oil and gas industry. The way it works is the flue gas is bubbled through the solvent, which selectively reacts with the carbon dioxide. The exhaust can be emitted to the atmosphere, and then the solvent, which is then termed to be rich in CO2, is cycled to another reactor, where heat must be input to release the CO2 and regenerate the solvent. And to get this heat, some of the steam from the power plant steam cycle is diverted. So this is steam that would otherwise be used for generating electricity. So this is where there's the major parasitic energy demand. So while this technology is mature in the oil and gas industry, there are some challenges and drawbacks in applying it to the power sector. The first is there's a significant scale-up required because of the huge volumes of flue gas we'll be dealing with. The second is the energy penalty, and another issue is there's other components in the flue gas, including oxygen and sulfur, which degrade the solvent. So there's a lot of ongoing work looking at these challenges. The next category, pre-combustion capture. This category integrates the fuel conversion with the CO2 capture. And it's based on a technology known as gasification. And so with gasification, the fundamental process involves heating up a fuel, typically at pressure, but in the absence of sufficient oxygen to completely burn the fuel. And what results is a mixture of combustible gases known as a synthesis gas, which includes the CO2. And the CO2 is separated from this synthesis gas. The synthesis gas can then be used, can be fired in a turbine to make electricity, or further refining can occur to produce hydrogen that may be used in future fuel cells. But the CO2 is in a different form, and so different solvents are used in this case, physical solvents that don't bond quite as strongly with the CO2, and so there's less of an energy penalty associated with the separation. Here there's a major energy penalty associated with pressurization of the process. Again, the gasification process is a mature technology in the form of integrated gasification combined cycle plants. There are examples of these around the world, and the capture technology is mature in the chemicals industry, but there isn't yet an example of this integration. That said, this technology is perhaps going to be the first example of the full-scale integration of CCS with power, and there's a plant under construction in the US and with plans for operation in 2014. So the final technology category is oxyfuel combustion. And so the first thing that happens here is that oxygen is separated from nitrogen in air, and this is typically uses cryogenic process, and this is an extremely energetic process. The advantage of burning fuel in oxygen instead of air is that the combustion exhaust is extremely concentrated in CO2 because it's not diluted by the presence of nitrogen in the air. So it mainly contains CO2 and water, which can vapor, which can be easily condensed out. This technology is also suitable for retrofit, which is an advantage. Compared to the other categories, it's perhaps a little bit further behind in terms of technology maturity. But there's some large pilot demonstrations around the world. Perhaps the largest is under construction in Australia. So throughout this description of the technologies, I've stressed the energy penalty. And this slide sort of compares them alongside, but it's presented in terms of the overall process efficiency, thermal efficiency. And so if we take as a reference a state-of-the-art steam cycle, these are about 45% efficient, and that means that the conversion of the heat energy associated with the combustion of the fuel to electricity is 45% efficient. If taking post-combustion as an example, we retrofit a post-combustion plant onto this steam cycle, then the overall process has a thermal efficiency of about 35%. And that, in fact, equates to a reduction in the power output of 20%. And another way of looking at it is we need to burn 20% more fuel to achieve the same amount of electricity. So the other categories compare quite favourably alongside post-combustion capture. There are sort of trade-offs across the different technologies, which I won't discuss today. And the numbers on the right look at sort of future projections. And some alternate future projections are shown here. And this shows the sort of the likely technology adoption trajectory. So technologies further down the track are characterised by the potential to significantly reduce the efficiency penalty, but they're also characterised by greater complexity. So the first round of CCS plants are likely to use amine-based solvents and these integrated gasification combined cycle plants with physical solvents. But then the next round, more advanced solid capture systems such as calcium looping are likely to come online, and this is the field that I work in. And to give you an example, this calcium looping technology, which are high temperature solvents, are currently being tested in a 1 megawatt scale pilot plant, so perhaps about 100th of the scale of a small pilot plant, but realistically 5 years off, whereas some of the further future technologies are still sort of at the laboratory scale, and there are many challenges to be overcome here, and sustained research is certainly required. So this takes us back to where we are today, and quite recently the Global Carbon Capture and Storage Institute did a bit of a stock take of all the carbon capture and storage projects going on around the world, and there's about 240 projects at various stages of development. However, a subset of these projects are what they define as large-scale integrated projects. And the criteria is given here, and of these large-scale integrated projects, there's about 80 at various stages of development. There are only 8 which are operational. And these are what are shown here in this table. And all I wish to point out is that pretty much all of these projects are in some way related to the oil and gas sector. So the capture technology is dominated by the separation of CO2 from natural gas, which is more straightforward than doing it from the exhaust of a power plant. And then most of the CO2 that's been captured is used for enhanced oil recovery. And there are plain economic reasons for this distribution. Another distribution bias is in terms of the geography, and so a lot of these plants are located in North America. And while a lot of governments around the world, in Europe, including the UK and Norway, particularly committing funds to this demonstration phase, the strategies in America are slightly more advanced, and a lot of the funds have been allocated to specific projects. And another reason for the distribution is also the maturity of the enhanced oil recovery market. So looking very quickly at the UK context, the government is certainly making big commitments to be a world leader in terms of reducing greenhouse gas emissions, including, as an example, the commitments this week to reduce emissions by 50% by the mid-20s. And at the core of this is investment required in new nuclear plants and renewable energy, but also CCS. So the role of CCS, well, the policy specific to CCS, there's a commitment for funding for up to 4 demonstrators. And the first project, the Longannet power plant, Scottish Power's Longannet power plant, has almost been allocated funds, and this is a post-combustion capture demo on 330 megawatts. And as Jeff mentioned earlier, there are other avenues for funding in the UK for these demonstration projects through the European Commission. The sum total of 4 demonstration projects of the scale of a few hundred megawatts is quite a way off where we perhaps need to be of the order of tens of gigawatts to meet the emission reductions. And so there's a lot of sort of policy development work required, and this is ongoing. DEC's about to release a UK CCS roadmap, and there's ongoing consultations in terms of electricity market reform, which is of a critical space at the moment. In terms of the global challenge, the International Energy Agency has also done a roadmap, and this is a figure from their roadmap, and it clearly shows the enormity of the challenge. Huge investment is going to be required to roll out an infrastructure that will surpass the size of the oil and gas industry. And in terms of projects, they project that 100 projects will need to be deployed on average every year from 2020. So there is a lot of optimism that CCS can enable us to achieve significant emission reductions in the context of continued use of fossil fuels, but there does remain uncertainty in terms of the technology that's been yet to be demonstrated in the power sector, and also uncertainty in terms of how we're going to pay for it, given the time constraints. But what I think we can be certain of is that this demonstration phase that we're at the beginning of, that's going to last about a decade, at least a decade, is critical, and all eyes are going to be on these demonstrator projects. So I'll finish it there.